Hi, in this video, I'll be continuing our study on probability. So in the previous video, we have defined what are probabilities and what's an event. In this video, I'll go through what is conditional probability and independence. So let's take an example to understand what we want to go through. Suppose you have two dice and we observe that the first die rolls a 3. Now that you have this information, what is the probability that the sum of the two dice equals 8? Well, there's at most 6 possible outcomes now that our event can occur, because dice 2 can roll from 1 to 6. But the way to get a sum of 8 is if the second dice rolls a 5. And so it's really still 1 over 6. And so what we want to say is that now we have a reduced sample space given our information. And so what's the probability that the event we want occurs within this reduced sample space? So let's say we let event E and F represent some events. Then the probability obtained is known as the conditional probability, given that some other event has occurred. So it's the probability of an event occurring given that an event has occurred. And really, if you think about it, it is defined to be the intersection over the probability of the event occurring. And that's what I've said. If you think about it, if you draw an Venn diagram, E and F here, you know that the blue area has occurred. So we want the probability that E is going to occur. But since we already know the blue area has occurred, we are actually just finding the probability of this red area occurring. And because it's a measure of belief, now we need to take it divided by the probability that F has occurred. And so it is known, if you know that the blue area has occurred, for E to occur, it must occur within the intersection only. And so that's why it's the intersection over the probability of the given event. And if you manipulate it, you can cross multiply, and you see that the probability of an intersection is the probability of event multiplied by the probability of E given F. And you can actually flip this around and say that the probability of E times the probability of F given E is the probability of E intersect F as well. And so what we want to think about conditional probability is that given information, how does it affect the future events that is going to occur? And generally, intersecting over n events is actually the probability of A1 occurring. And if you know that A1 occurs, then the next one is the probability of A2 given A1. Then it's A3 given A1 and A2, and so on. So you can really see it's how you're updating the information constantly. Another thing to take note is that because these two equations are equal, because they both equal to the intersection, we can equate them and divide one of the probability of A over. And so the probability of B given in A is actually the probability of B times the probability of A given B, which actually just equals the probability of A intersect B over the probability of A. And this is known as Bayes' rule. And this is really useful whenever you don't know what is the probability of B given A, but you know what is the probability of A given B. We'll see examples later on, but let me introduce you another formula first. And that is called the law of total probability. And intuitively, it makes sense because if you were to partition your sample space, which means that it's disjoint, which means that it's mutually exclusive, then the probability of an event occurring can be partitioned into in the same way. And so probability of B occurring is actually just the probability of B intersect A1 plus A2 intersection plus intersection of A3, and so on. And each of these intersection can be represented as a conditional times probability of AJ. And because they are mutually exclusive, you can just sum them all up by the axiom of probabilities. So here's the proof, which I've just verbalized. You can read it again for understanding. But it's clearer to see from a actual example. So for example, you know that a blood test is 95% effective in detecting a disease. But you also know that the test use of false positive means it tests a person with a disease to be wrong 1% of the time. A healthy person is tested. That is, if a healthy person is tested, the probability of having a disease is 0.01. And if 0.5% of the population have the disease, we want to know what's the probability that a person has a disease given that the test result is positive. So in this case, you know the probability of positive test result given that it's healthy is 0.01. But now we want to flip it around. So we want to know the probability of having a disease given that the test result is positive. And so that is the probability of the intersection over the probability of E by definition. And like I've said, the probability of DE is you can now condition on D, and so it's probability of E given D times the probability of D. And the bottom portion, the probability of E, can be broken up into probability of E intersect D plus the probability of E intersect D complement. And the reason why is because we already know what happens when you're conditioning over D, which is given in the information. And so you can calculate it out and see that it arrives to be 0.323, which is really unintuitive because you would think that the probability of having a disease given that the result is positive would be higher. But in actuality, it's only 0.323. And an intuitive understanding of why this is correct is given over here, given in the textbook by Sheldon Ross, probability first course in probability. I won't go through that because I think that you can just read it on your own and you can understand it. But what I really wanted to highlight from this example is the use of Bayes' formula, which is converting a conditioning from E to a conditioning of D, and then applying the law of total probability to the denominator to help break it up also. And then we move on to this thing called the Monty's Hall problem. And really, this is a very, very good example about conditional probability. And a very classic one. So, the Monty Hall problem is when, for example, you are a contestant. And there's this game host known as Monty who will let you choose one of the doors. And the thing is, in one of the doors, one of them will contain the car and two will contain the goat. And if you can choose correctly, you get to bring home the car. So once you choose, like, say, door 1, Monty will review the goat and the other door with the goat. So you could review, let's say, door 2 has the goat and door 3 has the car. Then he'll review door 2 and ask you whether you want to switch. And if he switches and he gets a car, then he gets the car in the end. So the question is, should the contestant switch? And let's define it clearly that the event that door I has a goat is GI, the event that door I has a car is CI, and the event that Monty's opened a door is MI. So if you do not switch, the probability of winning a car is 1/3 because at the start, if you do not switch, it's just the same as the probability of starting. But if you do switch, then the probability of winning a car, given that Monty opens door 2, is the probability that the car is in door 3, obviously. And so the probability, then you can use base formula to switch it around. So it's the probability now that Monty opens door 2, given that the car is in door 3, times the probability of the car being in door 3, over the probability of Monty opening door 2. And really, what's the probability of Monty opening door 2 when you know that the car is in door 3? Well, it's obviously 1 because Monty can't show which door is having the car. And the probability of having a car is 1/3. And for the bottom, you can use LOTP, Law of Total Probability, to break it up again. And you see that Monty opening door 2, given that the car is in the first door, which is the one you have chosen, is half because now you can choose either 2 or 3 because both of them have goats. Then you times 1/3. This has no chance of occurring. And lastly, you plus 1/3. And you see that the result is actually 2/3. And so, he'll win a car if he do switch. So, with that, he should switch. And really, if you see this tree diagram, it really explains to you clearly why you should switch. Because if you have chosen door 1, and the car is behind 1, 2, 3, is 1/3 each, he has a chance of opening door 2 or 3 in half. And so the outcome if you switch and you get a goat is 1/6. If you switch and you get a goat, it's also 1/6 here. But if so the total probability of getting a goat is 1/3. But in either case of getting a car is 1/3, and so the total probability of getting a car is 2/3 now. So the outcome of switching is more favorable to getting a car, and thus it leads to the reasoning of why you should switch. Lastly, I'll go through a quick overview of what is independent events, and really it just means that the outcome of one event occurring does not affect the other. And so the probability of E given F is the probability of E. And so what we really want to define is that the probability of E intersect F will just equals the probability of E times the probability of F. And that is because the probability of E intersect F equals the probability of E given F times the probability of F. And so E given F is the probability of E, and so that's why it's just probability of E times the probability of F. And so you're independent if the intersection equals to just the two probabilities multiplied together. And that is really just saying one probability does not affect the other probability. And if you're not independent, then you're known to be dependent. So let's take an example. So you have 2 coins and they are flipped. The probability of E having is the first coin landing a head, and F is the event that the second coin lands a tail. And this, of course, is independent because it doesn't matter whether you flip a heads first or tails next. And the event that the head occur won't affect the chance that a tail will occur. And really, you can prove this by saying the probability of E intersect F is 1/4, whereas the probability of E is half and the probability of F is half. And so you can see that the probability of E intersect F is equals to probability of E times the probability of F directly. And you can also prove that that if E and F are independent, then anything related to these two will be independent, and so E is independent to F complement as well. Here's the proof of it. You can read it for yourself to understand. And lastly, let me just go through what is conditional independence. So we have conditional probability, we have independence of events. Conditional independence is that you have two events and they are conditionally independent given a certain event if the intersection given the event is just the probability of A in given C times the probability of B given C. And that's really a very natural definition to give. And I'll give you an example to understand what it is better. But like to say that independent does not imply conditional independence, and conditional independence also does not imply independence. They are just like things that are conditions that can occur but they are not related. Like they only name the same, they only have similar names basically. And so we can take a look at this random coin example where the probability of a coin having a heads is PJ. So they are not equal now. So let's say you have an event, C is the event of having coin 1 chosen, and then you toss that coin repeatedly, and ith toss is H. Well, then the tosses are of course conditionally independent to each other given C, because once you have chosen a coin, then tossing it is just like tossing a normal coin. And so they are independent of each other given that you know something. And because you're given that you know something, they are known as conditionally independent. But the tosses won't be independent because if let's say HI is a H occurs, that means the ith toss is a H, the first toss is a H, the second toss is a H, it is affected by the coin that you have chosen. And so if the first one is a H, it might be more likely to have chosen C1 if the probability of having a H in C1 is very high. And so now you can sort of see that independence and conditional independence are not going to affect each other. Like having independence does not imply conditional, and having conditional does not imply independence. I hope this example gives you a clear picture of what is really conditional independence. But there's way more examples in the textbook for you to read up on. And if you want to really build a solid foundation, you can feel free to look through the textbook. I've come to the end of this video, and in the next video, I'll start on the journey of what is a random variable and go through some examples of discrete random variables. So I'll catch you in the next one. Thank you.